Hi everybody, I'm Greg Fishel and welcome to bonus weather video number 1 for this week. And we're going to be talking about a diagram that meteorologists have been using for many years, and it's incredibly useful and can be used for a variety of different purposes. But it's called a skew T log P diagram, and we'll talk about a couple of the reasons why it's called that. But just to have some fun with the words, it gives meteorologists info that is not skewed, which of course is very much appreciated. So let's log some time looking into this, shall we? Okay, so I'm going to give you an example of what the entire diagram looks like. And there it is. And there are all sorts of different lines on this thing. For instance, these brown lines are lines of equal temperature, and notice how they're not straight up and down or across. They're skewed, and so that's one of the reasons they call it a skew T-chart. Let's see, and then the lines of constant pressure are flat like this, okay? So you have 1,000 millibars, 950 millibars, 900 millibars, and so forth. Now notice that the distance between 1,000 millibars and 900 millibars is this distance right in here, okay? Up here, the difference between 200 millibars and 100 millibars is this distance here, much greater than this, okay? So the mass of the atmosphere is distributed logarithmically. In other words, the same amount of mass does not take up the same amount of space as you go up. As you all know, the density of the air decreases as you go upward, and so you have to travel a much farther distance to realize the same amount of decrease of mass, if you will, than you do down toward the ground. And so these lines of equal pressure become increasingly farther apart as you go up in the diagram. Okay, so let's zoom in here a little bit. And so this line of constant temperature here, this is minus 10 degrees Celsius, okay, which is about 14. And here's the freezing line, 0 degrees Celsius, and then you got 10 degrees Celsius on the positive side over here, which is about 50. Now, let's assume the weather balloon goes up at Greensboro, where they launch it every day, and we're going to say the surface pressure is at about 1,000 millibars. So what I'm going to do here is draw a line which is going to simulate what the weather balloon found on this particular day, okay? So got a big inversion, temperature increases with height, and then it gets to about here, and then it starts to decrease with height for a while, and then maybe doesn't decrease with height as quickly above that, okay? So this is what the weather balloon found on this hypothetical day. The temperature was about 14 near the ground, rapidly increased to about 32 up here, and then went back down again as you head up here, okay? Now, I'm going to pick a straight line tool here, and I'm going to make it parallel right along the ground, like this, okay? And then I'm going to go back to my freehand tool and draw a line down like this. When the sun comes up and it starts to heat the ground, then the ground heats the air above it, okay? And then eventually that air that is being heated begins to mix with air above it, and so the heating starts to become distributed over a deeper and deeper layer. But initially, when the sun first comes up, it's just working on this lowest part of the atmosphere here. So with this inversion being so steep, with the temperature increasing with height so quickly, the amount of energy required from the sun to get rid of this inversion is proportional to this area, and I'm trying to shade it in here, okay? So that amount of energy, that shaded area in here, is all that's required from the sun to get it from 14 degrees to about 36 degrees. Okay, and maybe you've noticed that on clear, calm nights when it gets really cold, when the sun comes up, the temperature jumps really quickly, and then the rate of increase slows down as the day goes on. Well, there's a good reason for that. So now what I'm going to do is I'm going to say, okay, we went from 14 to 36. Let's see what it's going to take to get us up to 50. Okay, so now I'm going to take my straight line tool and extend this line over to 10 degrees Celsius, which is 50. And then I'm going to take my freehand tool here, and if we get all the way up to 50, then this temperature line is going to have to be parallel to this dry adiabatic lapse rate. Okay? Now, the amount of energy required to get us to 50 is proportional to this huge area here. Okay? Much, much bigger than this area here, which got us from 14 to 36. So much less energy was required to go up 22 degrees than the amount of energy required to make it go up another 14, because in order to get it up to 50 degrees or 10 degrees C, that heat that is coming from the sun that is heating the ground now has to be distributed over this entire layer, which may be 5,000 or 6,000 feet thick, okay, as opposed to just trying to heat that shallow layer underneath the inversion, which doesn't require much energy at all, okay? Does that make any sense at all, okay? The bottom line is that when the air is mixed, then the temperature profile will be parallel to these dry adiabats, okay? And that's what we talk about. We talk about the dry adiabatic lapse rate, where the temperature goes down about 5.5 degrees per 1,000 feet, okay? And so that's what these lines that go like this are indicating, okay? Now, the green lines that you see here are called moist adiabats, and what happens there is that as the air rises, if it becomes saturated, then heat becomes released, the latent heat of condensation. And so then the temperature doesn't go down as quickly as it did when it was dry. And so the moist adiabatic lapse rate isn't quite as steep, but then once it gets into really, really dry air, then it's about the same as the dry adiabatic lapse rate, because there isn't much moisture present, so there's not going to be much heat released, if any at all, okay? So all sorts of things you can do with this. You can take a look at this for rain, snow, and ice situations. You can look at it for thunderstorms. And maybe once we get into some of these other scenarios, then I can go back to this and we can discuss how these diagrams are used in those typical situations. All right, that's bonus weather video number 1 for this week. Hope it made at least a little bit of sense. We'll have another bonus video coming up for you on Friday, and another daily update, of course, coming up for you tomorrow. We'll see you then. Take care, everybody.